The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next presentation is an update on EPRI concrete research by Kenneth Berry, Technical Executive of EPRI. Please welcome Kenneth.
Thank you. Great, thank you. I'm going to go through a wide range of topics that we're doing research on at EPRI, and specifically in a group called the Advanced Nuclear Technology Group. And it's going to be quick. It's going to be about a half an inch deep. So I'm going to talk about a few specific projects that we're working on, and then I'm going to go a little bit in the question about long-term operation. I'll talk about some of the research we're doing on that area too. First one we did, and this one is publicly available, is we were looking at the new build site. So I'm doing work for a company called, a program called the Advanced Nuclear Technology Program, and we are 100% focused on new nuclear build around the world. So we have members from utilities and vendors around the world that sit around the room and say, this is going to kill us. This is one issue that you guys need to work on. And what we're finding is that over the last 30 years, since the last time we built power plants in the United States, the codes for the building side really haven't been kept up. And so when we start talking about some of these issues, we say, yep, that's a code that really needs to be upgraded. And so that we can work through the research, get the code up to date, and then turn it over to the NRC to endorse it later on with some sort of reg guide or some regulatory action, so that we can then use them in the construction of the new build. As we're working on the VC Summer site and the Vogel site right now, some of those issues have been, some of those new technologies have been designed into the plans, but they're having to get special relief requests in order to use some of that technology. One of the issues we recognize is that this go-around for nuclear power construction, we are doing turnkey construction. So whereas VC Summer and Southern were actively involved in the design and construction of the plant last time, this time, they've signed a contract, and they basically are all trying not to get in the way. But ultimately, they're responsible for this plant when it's built. They're responsible to the regulator as the design authority to really understand what's going on. So this first product that we developed was a construction inspection guide so that the QA inspector at the utility, who's not a certified concrete inspector, who has not gone through all the ACI courses, can look over the shoulder of those guys that are qualified and make sure they're asking the right questions and make sure that something is not going wrong, especially when you're looking at a 51-hour base mat pour. You don't want something really wrong to happen when ultimately you're the utility that's responsible for it. So we wrote this guide, and basically this guide was just everything we figured out and we've got history on and OE, operational experience on, that we've screwed up in the past. We wanted to get it in a little document that the QA guy can stick in his back pocket, and he can be looking over the shoulder of the inspectors and the activities that are going on his site. So this thing is available to you. You'll see in really small print right there is a number, 300-200-520. If you went up to EPRI.com right now, you could download this PDF and print it out and actually use it on any civil site. But it really does focus on the nuclear industry. And we focused in on all the ACI codes that were relevant to safety-related pours, the ASME codes, and also the NRMA MCA codes. So it's not 1,300 pages of how you should be doing inspection on concrete. It's about 70 pages of everything we've messed up in the past, and you should be paying attention to if you're really concerned. We're also recognized that ACI, that high-strength rebar just wasn't available in the codes to a level that we needed for new nuclear construction. And so we started looking for a consortium that could do this work. So Mark is here from Charles Pankow, who has contributed a lot of money to this. The Concrete Reinforcing Steel Institute contributed, and also we're doing the research at the University of Kansas, and their Transportation Research Institute has also contributed money. So we have quite a consortium working on conducting tests on high-strength rebar for use in ACI 349 and 359. And so basically what we're doing is you can use higher-strength rebar right now, but you're only getting credit for the 60 KSI. And so we're started in 2012 looking at hook bars and doing the research for them. And then finally in 2013 we started looking at headed bars, T-heads bars, and then now this year we're starting to look at shear reinforcement based upon some issues that were happening at the new build sites in the United States. And so up to this point, the codes have used very little. There's some testing that occurred back in the 70s and 80s on T-heads and some higher strength rebars, but maybe 22 different tests that have occurred. We have already made, and you can see there's a picture of one of our forms. These things are about the size of a normal dresser in a bedroom, the size that we used. We have broken 250 of these blocks in the last couple of years. So we're collecting a wealth of knowledge on how high strength rebar behaves in normal size, normal types of concrete. We're doing 5, 8, and 11 hook bars, using 60, 80, and 100, also doing a couple of limited tests on 120, just to make sure that we got the equations right, and then the compressive strength of the concrete are 5, 8, 12, and 1500. What's interesting is that we've just had some extensive phone calls with Westinghouse, VC Summer, and Vogel sites, and we found out that most of the concrete in the AP 1000 is 4,000 PSI concrete. So the question is whether or not our equations will run down to 4,000 easily. We doubt they're using 4,000. If they're going to have some margin, they'll be using 5,000. So we're right there, but we're going to throw a few blocks in at 4,000 just to make sure we understand what's going on. This is a test rig. Basically what we do is we pour these things the size of a dresser, and we embed a hook or a head in there with a development length and cover based upon what we're trying to test, and then we take that rod and we pull it out of the concrete block and basically break it. So what's interesting is that we now have data, and we're getting more and more data. As you imagine, we have 250 blocks that were broken. So we know different size hooks. We can compare different size hooks to each other with different size amounts of cover. And so we can see what the behavior of this is. And we can now start looking at the ACI equations and say whether or not they're correct. And what we're finding out is that they're not. And so we're now providing that data back to the ACI committees to allow us to go back during next revisions, both 308, 318, and 349, to allow us to put really what's truly happening out there in the concrete world. So this is very interesting. We also now started doing the head test this year, and so we now have comparisons between heads and hooks, so we can then now match up a block that's very similar on the head size to the hook test, and we can see how they behave differently. So this has been very interesting. This is ongoing research. As I said, if you're interested in this, we have a quarterly report that we make public because we're trying to help the ACI codes know all of the information that's going on. First quarter next year, we're going to finish up this year all of our hooked tests, and first quarter next year we'll be putting out a report that we'll also be making publicly available so that everybody has all of our testing information. Another project that we've been working on is something also that's unique, I think, right now to nuclear construction, and this has to do with SC construction, which is steel concrete construction as opposed to rebar concrete construction. And basically the question came down from not only our regulator but other regulators as if we're going to use SC construction in these plants, can we detect voids inside these modules? So that was a pretty fundamental question. We do pretty well in just raw concrete and detecting voids pretty deep in, either using ground penetrating radar or other techniques that we can use. But the question is whether we can see through the steel plate. and from the steel plate, then through that interface into the concrete. And one of the issues that we've seen is that in the modular construction, that as the concrete shrinks during curing, that we sometimes get an air gap. And if anybody has dealt with ultrasonics and ultrasonic detection, that air gap's a tough one to jump when you're dealing with ultrasonics. And so it was an interesting question. So what we did is we made mock-ups. And we made some mock-ups in the labs, and this is one of the mock-ups that we have. And so we basically embedded, as you can see in here, we embedded various simulated voids inside the mock-up, but made this mock-up SC construction but also RC construction in the one mock-up so that we could see through the steel. We could also see through the concrete from the other side so we could actually detect. What's also very interesting here is that the science of making voids, mock-up voids out of styrofoam has also turned out to be non-trivial. As we started working on this, depending on whether you just put in styrofoam balls that were held together by mesh bags or whether you actually made surfaces on these things that would emulate what a void would look like inside of concrete. Both of those things became different techniques of detecting those things. So it was something that once we opened up the box, we realized everything was much more complex than we anticipated. But on this one, as you can see, some of the scans that we show on the left-hand side, we were able to pretty reliably detect that one void down there that's inside the SC construction portion in the lab in perfect conditions. So that was in anticipation for getting out in the field and actually trying to work on this. And so here's a true SC module. It's 3 feet wide. You've got the tie rods, the Nelson studs, and then you can see these are other voids. These were concurrent to that other mock-up, and the void technology that we learned in the other mock-up was not used in here, so these are harder to detect voids and not truly representative of voids that we see in concrete under normal construction techniques. This was a 3 by 3 by 10 foot mock-up. We had access to the steel from the side, but we also had concrete on the top that we could work on it. And then we had this other mock-up, which was a little more interesting, and this is basically the part of the shield building for the AP1000 in the upper region. As you get up higher up in the shield building, it has a vent tubes that allow the shield building to vent off to atmosphere, and this is in that region, and there are these rocket tubes that run through this thing angle here, where there was concern that from those areas that with the self-consolidating concrete could have some voids that would set up in that region. And so we had voids also embedded inside this thing as we made this mock-up. What we found in the field is that we really had a tough time detecting these voids inside these mock-ups. It was just, we used quite a few different techniques, and none of them were reliable in the field to detect these voids. So it's something, it's a work not finished. We need to go back. We need to set up some more mock-ups. We need to go into these things and work on these mock-ups some more and try to figure out maybe in a better environment what was going wrong. We were all pretty sunburned by the end of this week, so it was outside, it was in bright sun, and we had some challenges as we did this, but we were unsuccessful at reliably detecting the voids in these modules. Another report that we worked on was just looking at embedded sensors in concrete structures. And it was just a general question that came out is that, okay, 10 years from now, can we build these power plants with sensors that will allow us to have a better understanding of the degradation of these things for the life of the plant? And so basically, we started looking at what structure, or concrete structure, and this comes back into the question that came out on long-term operations, the subsequent license renewal. We started working with our long-term operations people to find out what degradation mechanisms were they finding as they started looking at these older plants. And we try to narrow it down because ultimately we don't want to instrument the entire plant. We want to instrument what we know is going to degrade and instrument it for the mechanisms that we know are going to happen. And so we started looking at all of the possible issues here, but ultimately we came down to the three. We came down to containments for strain, we came down to cooling towers for corrosion, we came down to spent fuel pools for leaks. So those were the main areas that we focused on in this report. And this report basically just is a compendium of all we know about sensors and all we know about what people have used sensors for in nuclear power plants. And so this right here is a good summary of all the power plants that are out there right now, nuclear power plants, that have actually censored themselves in the past. As you can imagine, when we start talking about doing this, we always have somebody in the room when we're having the vendors and the utilities talking about building a power plant that's going to last 80 years for $10 to $20 billion. The first comment that comes out is do no harm. Make sure that whatever you do, you don't make it harder for us and you don't make it harder for the existing plants, either through the regulator or through some other organization that's going to beat us over the head with some information that we just don't know. And so what we've done in this report is gone back to these plants, find out what they've done, have they been able to use this information to actually get actionable information out of the power plant and out of the sensors to be able to go back and say, yes, we have a degradation going on, and this is how we're going to fix it. If I'm going to instrument the base mat and there's no way I can repair that other than tearing the entire plant down, I don't need that information. We haven't had experience with the base mats having problems. But cooling towers, since we've had problems with degradation in cooling towers, can we instrument them so that we understand what's going on and maybe mitigate the problems that are happening before they start becoming a serious issue? So that's what we're looking at, and that's why this report has gone into extensive analysis of what's happened in the industry in the past and what we've determined. Also, on some of these plants, the sensors have subsequently, over 30 years, gone bad, and we're now looking at other technologies. Can we go back and re-instrument them with using surface technology instead of using embedded sensors? So it's an interesting report. As I said, it's mainly a compendium of what we've done in the past in nuclear power plants for sensors. So this slide, I'll let you look at this later in the interest of time. I'm going to skip through this thing, but basically what we were looking at is what sensors we were going to work on, how do we power these things. We always hear the transportation guys that they put sensors in on the bridges and they use the vibration of the bridge to power the sensor. Well, the last thing we want in a nuclear power plants is a consistent vibration going on. I mean, that's kind of that's the China syndrome movie, when they sit there, the coffee cup starts vibrating on the control room. That's not a good thing. So we're looking more at temperature as some way of sensing. You could also use radiation as a sensor, but that's also not a good thing too. So ultimately we really have to figure out ways of powering these things, and whether we go with RFIDs or passive RFIDs or something like that, that's another issue. But also the data collection side, whether we have wires or whether we go wireless, is another big issue. If we're inside containment and we're worrying about concrete's inside containment, we're always limited by the number of wires we can get out of the containment. So wireless is also a much advantageous approach to these things. Another one we looked at was quality control for fresh concrete. Since we had so many problems with voids the last go-around when we constructed 30 years ago and honeycombs, and as you can imagine, when we get into the basement, we have very dense rebar mats. That's the other reason why we're doing high-strength rebar, is trying to get rid of those dense rebar mats, but we start getting these voids occurring when we're building the power plant. So the question was, can we detect those when the concrete's fresh? So it was a great question, and so we ran off and did some research at Georgia Tech looking at 5 different technologies. We actually started off with 33 different technologies we thought could detect voids inside of fresh concrete. We narrowed them down, started whittling down, got down to these 5. And basically, as this report goes through, is that there was a new reg that came out that summarized that there was just a lot of problems with the power plants in the past when we built them, finding voids and honeycombs. You take the forms off and there it is. You go, well, what is that? Is that going to cause a problem over the life of the plant? You do an engineering analysis, you end up wasting a week of construction time waiting to figure out what to do with this concrete. We wanted to eliminate that. As we're building the power plants right now, we're spending $1 million a day. We don't want to be stopping and waiting to figure out whether or not we have problems. So the question was, can we do this? Can we build a vibrator that has a suite of sensors on it, and that would have a computer on board with a green light, red light? Because once again, the do no harm concept comes in here. The last thing we want to do is develop some sort of process that is going to slow the construction down, because we need to stop and get these vibrators out there and disrupt the process. And so we wanted to get this these vibrators that we just stick in, we're going in on 18-inch centers, and these things are just saying, yep, this is good, or no, we got a problem, vibrate a little longer to see if we can clear this up. That was the whole intent. Okay, so what we looked at was these different technologies. This chart, pretty busy, but signal-to-noise ratio, higher is better, and then implementability, higher is better. And we came up with a couple of ones that look like they might work, but this is all basic fundamental research right now. We've tried talking to the vibrator manufacturers to see if somebody would be interested in taking some of this technology and working with us to apply it, but we haven't got anybody's interest yet. But some interesting stuff. You can read through this thing if you want to go back later on and look at the technologies we worked. We were able, through ultrasonics, to actually detect them. Whether or not you could do it in the field easily, whether or not you could program a computer to figure this out, that's interesting, but we were able to do this. Sensitivity, we're getting to very long wavelengths, so that sensitivity for small voids it becomes difficult, but for the larger basketball-sized voids, which is really what we're looking for those type of issues, we could detect them pretty reliably using ultrasonics. We also had a couple of ones like conductivity, which are touch type sensors. So if you stuck the vibrator right into the void, it would know it immediately, and that was easy to do. But if it's 4 or 5 inches off or 10, 15 inches off, then that where we needed the ultrasonics, and we started looking at maybe we could instrument both vibrators and have them on 18-inch sensors talking to each other, and that would be another possibility going forward. But we need more research in this area. Some of the other projects we're working on, we're doing a lot of work in NDE for concrete. So we do a lot of NDE on metals, but we don't do a lot of NDE on concrete. So this void detection in SC, this void detection in fresh concrete is all being done by our NDE people. So looking for other issues, both corrosion, single defect, and pattern cracking, and what we can do going forward. Those of you in the nuclear industry will recognize Crystal River down here, and the delamination that occurred when they were doing a steam generator replacement there shut the plant down. So this is one of those premature shutdowns that you just don't want to have happen. So we're doing a lot of work to try to make sure that doesn't happen in the future. One of the ones that we're having a lot of success right now was trying to come up with a vehicle that would do automatic inspection of the concrete. So when you're inspecting a cooling tower, they're not small creatures here, the cooling towers. That's the basket of a bunch of guys being hung on the side doing an inspection. It's difficult, it's dangerous, it takes a lot of time. We're also seeing it in dams and on the containment. And we have this device here, it's called a crawler. It's not small, it's probably about this big, like a little go-kart. Using suction cups, and just goes up the surface. It can handle 90-degree turns. It can do quite a bit. It can handle a 40-pound payload. So we've now instrumented these things, and we can put this thing on an automatic run and just have it start running up and down containments and doing the inspection full time. So it's kind of an interesting technology. It's not anything. It's not any research we did, but we're taking and applying some vehicles that are out there. There's a couple of other ones that are available too, to try to make it easier for us to do inspections as we go forward. For long-term operations, one of the ones that we're running into right now is answering the question is what is radiation doing to the concrete, especially when we're talking about inside containment. And so this is one that we're doing core samples out of some of the existing plants that have been shut down to start trying to get some curves to show us what we expect based upon the fluence of radiation that the concrete's seeing, whether or not this is actually going to cause a problem when we go and try to license from 60 to 80 years. So this is another interesting one that I think will have a lot of help as we go forward on the power plants. Another one is ASR. So this is a degradation that we're seeing in the power plants alkaline silicon reaction. And while we now know what's going on, we know why it's happening, the question is, can we detect it, and can we reliably size it and know whether or not it's getting worse at an existing power plant that already has shown it? So we're looking at different techniques. Nonlinear ultrasonics looks like to be the most promising technique that we're doing, but we're making a lot of mock-ups. We're able to recreate it in the lab. We're able to now cause it to occur and to accelerate it, and now we're able to use nonlinear ultrasonics to actually detect it and size it. And so if you've never dealt with nonlinear ultrasonics, do what I do, Google it. There's always a Wikipedia page for everything you want to learn about, and there's actually a great one on nonlinear ultrasonics out there. Just read up on it. It's pretty fascinating how it's working, but we can use it to detect both radiation damaging, but also the ASR, which has been very helpful as we've been going forward. This is a good chart showing you the ultrasonics, nonlinear ultrasonics, and showing you that how quickly, as it starts advancing, how it does show a pretty good indication that there is something wrong with that concrete, and we can size it and watch it progress as we go forward. So this is new technology and promising technology, but we're using it at the power plants right now for those that actually have ASR going on at this point. Another big area is, especially when we're talking about long-term operations, is the spent fuel pool. We've had numerous instances around the world where we've had leaks through the liner plates in the spent fuel pools. They're borated water, so it's a corrosive environment. And then once it gets into the concrete and gets into the rebar, it starts corroding the rebar. Rebar starts to expand. It starts to cause the concrete to crack, and then we start having more problems with that. During our sensor project that I talked about earlier, we were looking at ways of drilling through the back end of the spent fuel pool and instrumenting the concrete that way so that we could detect whether or not there is water occurring in the concrete and whether the rebar is actually starting to expand. So this is something that's it's interesting and something it's a problem for nuclear power plants and something that we're continuing to work on. And then chloride tack on the cooling towers is something that continue problem at the power plants. And also, as we build new nuclear power plants around the United States, cooling towers are now almost required as we go forward. Water is the big issue for nuclear going forward, water availability. We're not going to be able to pull from streams and do once-through cooling anymore. So we're going to see more and more cooling towers. And so understanding better how the cooling towers are degrading is kind of critical to us right now. We had that discussion earlier about the nuclear renaissance and what happened to the nuclear renaissance in the United States, and there's 71 nuclear power plants being built around the world right now. So that's a pretty good renaissance. It's not happening so much. We only have 5 in the United States right now, so we're slow starting. We'll get going in a couple of years once we see this first group. But around the world, Russia, China, other countries are building very rapidly right now. So it wouldn't be a bad thing for you to toast the nuclear renaissance tonight during the reception, because it really is happening, and we're going to see more and more nuclear around the world as we try to reduce CO2 from all the other power plants, the fossil plants. So with that, I'll stop and answer any questions. Remember, as I said, I'm going about a quarter-inch, half-inch deep on each one of these topics. We've got quite a few different areas that we're doing research on. I've got business cards. I can email you more detailed information, and also for the ones that are publicly available, I can show you how to get them downloaded from the EPRI.com.
Okay, any questions?
Are you doing any fly ash research?
Are we doing any fly ash research? So on the nuclear side, we haven't done that much work on it. It seems like every university in the world is doing some fly ash research, so we just haven't spent the money. We feel that that's being covered pretty well, and we haven't spent that much time on that. Yeah.
Okay. I'm going to have to cut off the questions here to move on. We have time for maybe one more. Mike?
How are you protecting the steel plates on the steel concrete construction? The steel plates are exposed.
How are we protecting those? How are we protecting the steel plates? That's a construction issue. I don't think they're protecting them at all. Some of these things are just, these are just modules inside of buildings, and so if it's inside a building where you're going to epoxy the floor or do concrete down, then they're going to be pretty well protected. The shield building for the AP1000 is external, and that's SC Construction. I'm not aware of any coatings that they're placing on the outside.
Very good, Ken. Thank you very much. Thank you. Thank you.